Lesson 3-2, Measures of Variation. The objectives: develop the ability to measure variation in a set of sample data by finding values of the range, variance, and standard deviation. Develop the ability to interpret values of the standard deviation by applying the range rule of thumb to determine whether a particular value is significantly low or significantly high. The first part, you probably have done range before, maybe not on variance and standard deviation, but you've probably not done the range rule of thumb before. Variation is the single most important topic in statistics. Basic concept of variation: an important goal of business and industry is to improve quality by reducing variation. Range. Range of a set of data is the difference between the maximum data value and the minimum data value. Properties. The range uses only the maximum and minimum data values, so it is very sensitive to extreme values. The range is not resistant. So it is not resistant. Make sure you underline that, not resistant. Because the range uses only the maximum and minimum values, it does not take every value into account and therefore does not truly reflect the variation among all of the data values. So it only does the, the gross variation or the global variation, and not really the local variation. Range is the max data value subtracted by the minimum data value. So let's, I'm sure you've already done this before, but I'll give you a couple, let's see, 38.5, 55.6, 22.4, 14.1, and 23.1. So what we want to do is we want to, the range is going to be the largest value, which in this case is 55.6, minus the smallest value, the minimum data value. In that case, it's going to be 14.1, and then let's see. So what does that turn out to be? 55.6. 55.6 minus 14.1, 41.5. So in this case, it is 41.5. All right, good. The next one is the standard deviation of the sample. Some of you may have done this one before, some may not. It's not super difficult. It is denoted by the symbol S. S. The symbol right here, S. And it's a measure of how much the data values deviate from the mean. The formula is S equals the square root of the sum of x minus x bar squared divided by n minus 1. And that's for a sample. A sample. That's for a sample. Properties. The standard deviation is a measure of how much data values deviate away from the mean. The value of the standard deviation S is never negative. It is 0 only when all of the data values are exactly the same. Larger values of S indicate greater amounts of variation. S can increase dramatically with one or more outliers. The units of S are the same as the units of the original data values. S is a biased estimator of the population standard deviation, sigma, which means that the values of S do not center around the value of sigma. So in this Greek letter here, I didn't do it real good. That is called sigma. All right, sigma. So how do we do one? Well, I had some values just a minute ago. Let's I'll put some of those back up. Let's see what we got here. We've got some values, and what if I made a table? Let me make a table, and let's see here. How many values did I have before? Let's see here. We've got 38.5. We have 55.6, 22.4, 14.1, and 23.1. Okay, so we're going to calculate the standard deviation of these. And I'm going to do it in table format. Maybe that'll make it slightly easier. So the first thing I need to calculate is the mean, right? So how do I calculate the mean? Well, I got 1, 2, 3, 4. I have 5 values, right? 5 values. So I need to add those up. So we have 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1, and that equals 157.3. 157.3, that's the total. Now, we're going to divide that by 5, so our mean, x bar, is going to be 157.3 divided by 5. Divide by 5, and I get 30.74, which is 30.74. Now, let's look up here and see what we need. Let's see what we need here. We need the sum of x minus x bar. So we're going to have x minus x bar squared. So we're going to have 38.5 minus 30.74, and we're going to square that. Here we're going to have 55.6 minus 30.74, and we're going to square that. Then we're going to have 22.4 minus 30.74. Square that. 14.1 minus 30.74 squared. And 23.1 minus 30.74 squared. And we'll see what those equal. So let's see. Open parentheses, 38.5 minus 30.74, close parentheses squared, 60.2176. 60.2176. And let's do the next one. Open parentheses, 55.6 minus 30.74 squared, and that's 618.02. 618.02, and we just got 3 more. Let's see here, 22.4 minus 30.74 squared, and 69.5556, 14.1 minus 30.74, 276.89. And then let's see, the last one, 23.1. Let's see here, 23.1, is that right? 23.1 minus 30.74, close parentheses, 58.3696. 58 point, is it 3696? 3696. Now I'm going to add up this total here, add those up, and I'm going to cheat a little bit. I'm going to use the old plus plus and that'll kind of reduce my rounding there some. And I get 1083.05. 1083.05. So that's this right here. This is that's that right there. The sum of x minus. All right. So now I'm going to put that. Let's see. We got the square root of 1083.05, and then n, that's going to be 5 minus 1, which is 4. So let's go do that. Control square root, control divide, and then I'm up here in this. So I'm going to go up there and oops, I'm going to grab that and then divide that by 5 minus 1, and I get 16.45. 16.45. Okay? 16.45. Now I rounded, I went 2 decimal places because this is 1 decimal place, right? So I want 1 more than what I should or had to. All right? So that's standard deviation. And yes, there's an easier way, but we'll concentrate on doing it by hand with the small numbers so we get appreciation when the calculator does it with the larger group. All right. The range rule of thumb. Significantly low values are values that are x bar minus 2 times the standard deviation or lower. Significantly high values are x bar plus 2 standard deviations or higher. Values not significant are between x bar minus 2 times the standard deviation and x bar plus 2 times the standard deviation. All right. So let's take a look at it. What if, say, and that data was all about internet speeds, megabytes per second. Okay, and what did we find out? We found out that, we found that our standard deviation was 16.45, and our mean was 30.74. So let's put that there. Our mean x bar was 30.74, and our standard deviation was 16.45. Now, I don't know if you know it or not, but we'll say Verizon has come out and said that, hey, we now have one that runs at, we'll say 77.8. Verizon now says they have one that runs at 77.8. Well, is that significantly high or significantly low or whatnot? And can we tell? Well, using statistics, we can. Listen, we got X bar is 30.74. And what's this high right here? So let's go 30.74 plus 2 times and 16.45, our standard deviation, and that gives us 63.64. So this is 63.64, and this here, that's going to come in over here somewhere. So that is significantly higher. Okay, Verizon has outdone themselves. They have made something that is significantly higher. The next thing is the population. The population standard deviation. It is. Let's see. We got this new symbol here, and this is mu. It's pronounced mu. Okay, and that is the population. That's the population mean. Okay, and then X, of course, is the individual data value, and N, capital N, is the population number or count. Okay, how many is in the population? So, big difference is with the sample, we do N minus 1, and with the population, we don't subtract 1. Variance is a measure of the variation equal to the square of the standard deviation. Sample variance, S squared, square of the standard deviation. Population variance, sigma squared, or the square of the population standard deviation. We actually found that before on the sample variance. We actually found that before. Let's see here. We actually found that before. And if we'll go back here, and that was 1083.05 divided by 4. That would have been the variance, or S squared. S squared. That would have been the variance, okay? $10.83 control divide 1083.052 times divided by 4, 5 minus 1, and that's 270.763. It would have been 270.763. All right. Properties, the units of variances are squares of the units of the original data value. The value of the variance can increase dramatically with the inclusion of outliers. It is not resistant. The value of the variance is never negative. The sample variance, S squared, is an unbiased estimator of the population variance, which can't really be said about the standard deviation. Okay? The empirical rule. Okay? Now, this is actually it's kind of in your calculator. But I'm going to draw it out, and you probably need to put it in your notes. Now, you may have seen this in Algebra 2, but we're going to be a bit more precise here. So we have, and I'm on a dotted line here. We have right here in the middle, okay, and this is X bar, right? That's X bar. Well, on this side here is 50% of the data, and on this side here is 50% of the data. Okay. Now, if we go here about right in there, and about right in there. We have, this would be x bar plus s, and this would be x bar minus s. Okay, now in algebra 2 we said that was 34%. It's actually 34.13%. Okay, and that's 34.13%. And that's just one standard deviation. If we go two standard deviations, and that's going to be about right in here, I believe. And again, it's going to be about right in there. And we're going to call this x bar plus 2s and x bar minus 2s. And in this is 13.59%, 13.59%, okay? And then the next one is going to be about right in there, and about right in, still off a little bit, trying to be fairly precise for you. And then we've got x bar plus 3s and x bar minus 3 standard deviation. And inside here, that's going to be 2.14%. And this is going to be 2.14%. And of course, over here, you're going to have 0.13%. And over here, you're going to have 0.13%. Okay? Now, what this says is this first standard deviation, and we'll say, let's see here. We're going to say here, from this line here and to there, we're going to say from there to there. And you know, I want a solid, well, let's see here. Do something a bit thicker. And we'll say from here to here, that's plus or minus 1 standard deviation. Plus or minus 1 standard deviation. That's 1 standard deviation over here, 1 standard deviation, we call it 1 standard deviation. And it is 68%. Okay? 68%. Next, and let's see here. Let's get I don't like that one. I like that a bit. Green. Let's go from and that's going to be from here to here, and we're going to say that is 2 standard deviations. Get that green. This is 2 standard deviations. And that is going to be 95%. We'll put 95% right there. All right. And then the third one we're going to be looking at, and let's see here. The third one we're going to look at, and let's see. Let's just do it in black. We're going to go from here to here, and we're going to say that is 3 standard deviation. Three standard deviations. and that is going to be 99.7%. Okay, so what that says is 68% of the numbers should be within one standard deviation of the mean. 95% of the numbers should be within two standard deviations of the mean, and 99.7% of the numbers should be between three standard deviations. And that is the empirical rule. Okay? The empirical rule. It is extremely important. Chebyshev's theorem applies to any data set. The proportion of any set of data lying within k standard deviations is always at least 1 minus k divided, or 1 divided by k squared, where k is any positive integer, positive number greater than 1. Okay, this is the standard deviations for non-normal data. Okay, it's rarely, if ever, used, but I wanted to introduce you to it. Okay, for k equals 2, and at least 1 minus or 3/4, 75% of all data lies within two standard deviations of the mean. And for k equals 3, 89% of all values lie within three standard deviations of the mean. And so that's 75% compared to 95%, and 89% compared to 99.7%. All right? So that's Chebyshev's theorem. Coefficient of variation. Sometimes, for a set of non-negative sample or population data expressed as a percent, describes the standard deviation relative to the mean. What if you wanted to compare the variation between two data sets, and maybe they're not the exact same thing? Okay. Yes, I have some samples for you. All right. So what if? Oh, looky here. We did 5. Those are the 5. But this time I've got like 50 of them from Verizon. Okay, so there's a whole bunch. Let's find the mean. Let's find the mean. So I'm gonna got it right here, and I'm gonna say menu 4 1 1, and then number list is 1, and we're gonna use data. Okay. And there we go. So 17.59, that's for all 50. Basically, we'll say 17.6. Okay, so we got for Verizon, we have 17, let's see here. X bar is 17.6, and S is, well, let's go find it. Isn't this much easier? So S is 16.02. So we got 16.02. And then we're going to compare earthquakes to earthquakes. Yeah, earthquakes to Verizon's data speed. All right. So let's go here, and we're going to do, now, this one here, you'll look, I got 600 numbers in here. Yeah, let's see. Yeah. And then, yeah, I mean, I got 600 numbers in there. Okay. I love technology. It's great. Watch this. Menu 4 1 1. What if you had to do that by hand? Number list is 1, and we call it Earth this time, and we'll put the color, there it goes. So our mean is 2.57. So X bar is 2.57. What is S? What is S? S is 0.65. 0.65. So we're going to compare the variation in the, we're going to compare, let's see here, we're going to compare the variation among data speeds and the variation among earthquake magnitudes. Okay, see which one has more variation. So the coefficient of variation for Verizon is going to be, we see S, that's going to be 16.02 divided by X bar, that's going to be 17.6 times 100, and that's going to equal 91.0%. All right, the coefficient of variation for earthquakes is going to be 0.65 divided by 2.57 times 100 equals 25.3%. Okay, so we can see that the Verizon data speeds vary considerably more than earthquake magnitudes. Isn't that cool? All right. Great job, folks. Oh, biased and unbiased. That's right. Put this in your notes. The sample standard deviation S is a biased estimator of the population standard deviation, which means that the values of S do not tend to center around the value of sigma. S tends to underestimate the value of sigma. And it's even worse if you didn't do n-1. The sample variance S squared is an unbiased estimator of the population variance sigma squared, which means that the values of S squared tend to center around the value of sigma squared instead of systematically tending to overestimate or underestimate sigma squared. Okay, that's all the folks, that's all the notes for tonight, folks. Have a good evening, and I will see you tomorrow in class.